In this lecture, we look at a procedure by which we can identify the amount of phosphorus in a soil under field conditions when we are right out in the field. And this is known as the quick P field test. Basically, it's a field test and not a lab test. Now, what is the quick P field test? The quick P test is based on the phosphomolybdate blue procedure of Murphy and Riley. It has certain advantages because it can be done at the field site. Rapid turnaround reduces expenses involved in soil sampling and analysis, and decisions on sampling locations can be made in the field without bringing soil samples to the lab. So it's actually very convenient when a group of researchers, a group of extension agents go out into the field and they would like to know the concentration of P in a particular location. It can be tested very quickly by the quick P field test. We'll be describing that test in a little bit more detail. Now for the PQT, that is the P quick test methodology, the reagents are 0.1 molar hydrochloric acid. Then we have the usual reagent A and reagent B. For the 0.1 molar hydrochloric acid, dilute 1 ml of concentrated hydrochloric acid, which is actually 12 molar, with 120 milliliters of water. Remember, you always have to put acid into water and not the other way around. And this should be done under a fume hood. Reagent A, to obtain that reagent, we have to dissolve 6 grams of ammonium molybdate in 100 ml of distilled water. Dissolve 0.1454 grams antimony potassium tartrate in 25 milliliters of distilled water. Dilute 72 ml of sulfuric acid in about 750 ml of distilled water and allow to cool at room temperature. To the room temperature sulfuric acid, add the ammonium molybdate and the antimony potassium tartrate. Take to 1.0 liters with distilled water, mix thoroughly, and store in the dark. This is the reagent A, which you can take to the field. Reagent B. Dissolve 0.15 grams ascorbic acid in 10 ml of reagent A. Make the reagent B on site and store in a cool, dark place while running the tests. Now, all reagents must be placed in a cooler when transported to the field site. In other words, you prepare reagent A in the lab, take it with you to the field. Reagent B, you just bring in the material, prepare it at the field site. So in the field, take about 1 gram of the soil sample in a porcelain plate. The plate is shown in the picture here. Add 0.1 molar hydrochloric acid, drop by drop, until the soil is just saturated. Mix with a glass rod to force wetting before bringing to saturation. Now tap the side of the spot plate to settle the soil and allow the solution to rise and pond on top of the soil. Allow the saturated soil to stand for 5 minutes. Use a glass rod to transfer 1 or 2 drops of solution into an adjacent well. Now, before I move further on the procedure, just let's take a look at the spot plate. Now, the row to the extreme top, the top row, is the various soils that you have collected. Soil number 252, 53, these are just random numbers, and they are taken by depth in this case. And the second row of plates, the second row is kept free. That is, there will be no soils on that, because there should always be a row for developing the color. Then the bottom 2 rows would be for a second set of soil samples, 258, 259, and 260. And of course, the last row is for developing the color. So this is how the color is developed on a spot plate. Soil samples are from the various depths within the soil profile. Top left is the surface soil. And the 260, number 260, will be the deepest soil that we have taken in this particular case. Now, once you have the glass rod and you have tapped the solution into the adjacent well, that is the 250, for example, the solution is tapped into the well just below that, and then you add a 1 drop of color reagent to the upper side of the spot plate well. And then that means that color reagent will develop and give you a blue color. Check for the intensity of blue color in 10 to 15 minutes. Now, if you look at the plate itself, now we are going to look at the second line, the second row, and the last row. Remember, we have taken the soil by depth. So what do we notice? The color diminishes as we go from 250, that is the topmost left well, and then it just diminishes. The color fades with depth, suggesting that only the surface soil is P impacted in this particular case. Now, we need to have some sort of comparison of the relationship between PQT and Mehlich 1P, or as currently we could test it with Mehlich 3P. This is a P impacted poultry location. Look at the Mehlich 1P values. They're very high. They range from 0 to 400 on the x-axis, and on the y-axis is the depth to which of soil sampling. We went up to about 80 centimeter depth. But the soil samples were taken in the field at 5 centimeter intervals. Topsoil at top left, lowest depth is at the bottom right. Bulk soil samples from the corresponding depths were brought to the lab and Mehlich 1 analysis conducted. Now, note that the color developed in the field corresponds closely to the analytical values, with color fading at about 50 centimeters. No color appeared after the 60 centimeter depth. Now, if you look at the Mehlich 1 value, the value that corresponds with the first well there is about close to 400 milligrams per kilogram, decreases gradually, and by the time it reaches 50 centimeter depth, the color, the Mehlich 1P, becomes essentially 0, and that corresponds very closely to the solution without any color in the field. Now, it is not possible to get anything more accurate than this in a field. That means you know almost at once where the background level of P is. In other words, how much the P would have moved in that particular soil profile. Now, here is PQT and Mehlich 1P for a P impacted dairy location. Here the impact level is much lower than the earlier one. It's just around 15 milligrams per kilogram of P, and the depth is the same. And what do you notice? The color fades. The color is much lighter than in the previous, naturally, because the concentration of P is much lower, but it fades about 80 centimeters. And this is where the PQT doesn't show any more P in the field, and the Mehlich 1P becomes 0. You will notice that it's funny that the reduction in color intensity at the 5 centimeter depth is also captured by the PQT method. It is so accurate that it captures even that reduction in color at that particular low Mehlich 1P concentration. Now, here's something to look at. Depth of P movement as obtained by PQT and as a function of depth by Mehlich 1P. Intact soil cores were taken from dairy and poultry manure application sites, and the depth to background P, that is when no more blue color was detected by QT, compared to 0 Mehlich 1P. And what do we notice here? Get an almost perfect 1:1 line, showing that PQT corresponds very closely to Mehlich 1P. So what you do out in the field is very close to what you would do in the lab. You get almost identical results. So when you're out in the field, you can almost say exactly to what depth your phosphorus would have moved. It's very easy to discuss such results out in the field along with colleagues while you're discussing the P impact at a particular site. Now, we'll look at another type of relationship that is between PQT and water-soluble P. Water-soluble P, water extraction P, we have looked at it, the procedure in an earlier lecture. And we look at the correspondence of the field estimation of P by PQT to a meter depth compared to water-soluble P, determined in the lab. And you'll notice that the depth to background P levels corresponds pretty closely to water-soluble P as well, water extractable or water-soluble P. And therefore, the PQT is a very good field determination of the depth to which the phosphorus has moved. Here in this diagram, in this slide, you will look at a situation in a dairy field. The top left plate is what happened before effluent application, and below is what happened after effluent application. And we're just looking at P concentrations as detected using the PQT a year after heavy P additions. Now what do you notice? Prior to the manure effluent P, there was some blue in the surface horizons, maybe the first 2 depths, and it then reduced, the color then reduced. So there was not much of a P impact below the surface 2 depths perhaps. But what do we see after that? After the manure effluent, it is a year after, we repeated the PQT at the same site. And now we find that the PQT has moved to much, much lower depths, say about 40 or 45 to 45. It's interesting that the 35-40 depths, the color is low. It's probably in contact with a material, a soil that has very little P retention capacity. Now, look at this. This is a very easy way that we can do out in the field the difference and notice the difference between a before and after, or we can do it between an unimpacted or an impacted area or P impacted areas with different P impact levels. You can do all this out in the field without bringing the soil into the lab. Now just a few comments here. The PQT is a simple field test that corresponds well to Mehlich 1P or water-soluble P, both of which we have discussed earlier. But there's a detection limit of PQT. Below 1 milligrams P per liter, it appears colorless. And above 15 milligrams P per liter, the solution appears very dark blue and changes in color intensity, not easily discernible. You know it's high, but you cannot get an exact value. Check soils of known Mehlich 1P could be introduced in the spot plate for comparison of color intensity when you're out in the field. That means you take with you a few samples of soils for which Mehlich 1 concentrations are known. That means they have been determined in the lab, and you can use that as check soils when you're out in the field. Now, the other thing to notice is experiments should be done in the shade to avoid solution drying on the spot plate to produce a blue-green color. Now remember, you have to take the reading or look at the color development within about 10 to 15 minutes. If you keep it for too long, it is going to dry up in the plate. But remember, the PQT is not a substitute for P determination by lab procedures. You still need to do your Mehlich 1P or a Mehlich 3P or your water-soluble P for more accurate lab results for publication and other purposes. But again, you can repeat, the PQT is a very handy procedure to do out in the lab, perhaps particularly when you want to discuss the P impact at a given site. Now, a couple of references here. The first is a common reference, well known. It's a Murphy and Riley procedure. And the second is a quick field test for evaluating phosphorus movement in sandy soils that was published by Dr. Rue and others in the New Zealand Journal for Agricultural Research. And with that, we end up with this lecture.